Good to go. All right. Okay. So, hello everyone. This is Makan Karger, and we are pleased to welcome you to do the fourth talk of GNSS-IR webinar series. This is organized by IAG Working Group on ground-based GNSS-IR application for climate study. So today we are very happy to have Dr. Surui Xie from University of Houston. He will talk about GNSS-IR application, as we can see here, for polar coastal research and see IceFreeboard measurements. So it's going to be very interesting and important application of GNSS-IR for polar research, and I'm happy that Surui giving a talk about that. So just a little bit introduction about Surui. Surui is a geodesist by training, as far as I know. He received his bachelor in geodesy and geomatics engineering from University of Wuhan in 2011, and then a master degree from the same university in 2014. And he got his PhD from University of South Florida in Tampa in 2020. And then he moved to Scripps from 20 to 2022 and did his postdoc there. So his research mainly focused on using
Hello.
geodetic techniques to study crustal deformation and sea level change. So this talk will last around 40 to 45 minutes, sorry. And then we have around 10 to 15 minutes time for question and discussion. Please feel free to write your question in the chat box during the talk. And at the end of the talk, you can raise your hand if you would like to speak and ask your question directly. Please do so. So if you like to stay updated, as you can see here with news and future events, please feel free to subscribe to the working group mailing list shown here. So yeah, let's get started. Suri, over to you. I stop sharing.
All right. Let me share my screen. Well, thank you so much. I'm glad to be here, presenting some of the work I have done over the last few years. Uh,
Yeah, you are in presentation mode.
okay.
Small is small. Still a bit small. Yeah, there you go.
How about
Perfect.
now? Is there a
Nice.
way to to switch the? If I do this,
It's going to be like dual screen and one big and one small. So the previous one was better.
okay, let's use that. Uh, all
Yeah,
right.
that's much better.
Let's try. Okay. All right. So today I'm going to introduce some of the GNSS-IR related work I have done over the past a few years. My collaborators include Christine Larson and Thomas Leland at DTU. All right. First of all, let's talk about elevation measurements. Elevations are the most fundamental information about our Earth. Repeated measurements of elevations can help us quantify some of Earth's surface processes. Um, there are three representative techniques that can be used to measure surface elevations, while including the elevations of sea surface. Um, Here on the left, lower left, this is a figure showing the concept of GNSS positioning. Um, Here, GNSS it's a generic term for satellite positioning and navigation system. It stands for Global Navigation Satellite System, including GPS. That's perhaps one of the most widely used GNSS system. It allows us to measure elevations with high precision. If the GNSS receiver is placed on a sea surface platform, then by tracking GNSS, we could determine sea surface elevations as well. This technique can provide very high sampling rate, but it's limited at fixed points. Another widely used technique that can be used for repeated elevation measurements is using tight gauges. This figure illustrates a tight gauge. This is either an acoustic sensor or a laser sensor or radar sensor. It measures the distance between the sensor and the sea surface. There are other types of tight gauges, including the one that can be placed on the sea floor, which is sensitive to sea level associated pressure changes. This technique also provides very high sampling rate, but it's limited to a specific size, and the daytime control is required to maintain long duration observations. Neither of these two techniques can provide a very good spatial resolution. To do that, we can use satellite altimetry. This technique can cover nearly entire Earth. Perhaps in the polar regions, there are some gaps, but overall, it provides very good spatial resolution. And though the temporal resolution is limited, and this is one of the major data source for quantifying global sea level change. Here, this map shows the global distribution of traditional tight gauges in the GSLOS system. We could see that these tight gauges, they are not evenly distributed, and there are very few stations in the polar regions. Well, about half a dozen in Greenland and about a dozen in Antarctica coastal regions. This figure illustrates the spatial coverage of satellite altimetry. This technique provides high spatial resolution, but there are gaps in the polar regions, mainly constrained by it's mainly due to the limitation in satellite orbits. So it measures sea level up to about plus minus 66 latitude. We could see that the majority of Earth's ocean is measured by this technique. There's a small portion, well, perhaps a fraction of the ocean that is not covered, mainly in the southern ocean and the central Arctic Ocean. Though there are efforts trying to fill the gaps, however, in the polar regions, sea levels are seriously undersampled. When we estimate sea level change, usually the global mean sea level rate is the value that is reported. In determining that value, ideally we should have measurements all the ocean and evenly distributed. But due to the limitation of satellite altimetry and tight gauges, there are fewer observations in the polar region compared with the other parts of the global ocean. Apart from the coverage, There's another problem in the polar regions if we want to determine sea levels. Uh, well, here let's play the there's an animation here. Yeah. So in the polar region, sea ice coverage, sea ice and snow coverage and thickness, is time dependent. Because of that, sometimes if the polar region if it's measured by satellite altimetry, we might need to consider the effect. And some of the data can be useful, particularly when the sea surface is ice-free, but sometimes it is covered by ice. In that way, we need to think of ways to eliminate the influence of thin ice. Um, and also, thin ice could also affect the measurement of tide gauges. I spent about 14 to 15 months in Antarctica. My major job was to, well, one of my duties was to maintain a pressure tide gauge, and that tide gauge it was placed near shore, and the cable was frequently damaged by sea ice. So sea ice pose threats to tide gauge measurements. And also, this technique requires data control, which is difficult in the polar region due to the challenges in field logistics. Mm, for sunlight signal, they could be well, sometimes it's ice free, sometimes it's ice covered. So it is challenging to select the useful data to quantify sea level changes. Um, on the other hand, sea ice extent and thickness themselves, they are some of the interesting quantities for scientists to measure. It would be great if we can measure both sea level and sea ice um, accurately. Talking about sea ice and thickness measurements, there are two major techniques um, in situ methods, including a traditional way of drilling holes on thin ice, and then just use a tape measure to measure the thickness. It is robust, but it is labor intensive, and it can sometimes be unsafe. There's another way of in situ method that is using electromagnetic induction devices or mass balance buoys. These techniques they work fine if you pre-install the sensors in sea ice. So these techniques they have some limitations in the observational period. Um, for instance, in summer, in polar region summer, you might lose your sensors, and these sensors can also be crashed by the motion and deformation of thin ice. And these techniques they are restricted to point measurements. Remote sensing techniques can provide basin-wide sea ice thickness measurements. Um, uh, the major technique, including using the difference between satellite altimetry measurements and calculated sea surface, or using the lead measured by satellite altimetry. So this makes the assumption that sea ice is in a hydrostatic equilibrium state. This technique is good. It's great to provide a wide coverage, but it has limited temporal resolution due to the long revisit time. And in some coastal regions, it is challenged, mainly due to sea ice deformation and the contamination of land reflections. Um, well, many years ago, before meeting Macron, I spent about 14 to 15 months in Antarctica. Um, Here on this one is me on the left or on the right, and that's my colleague Jie Zhao. He was an oceanographer, so he cares about sea ice growth and evolution, and he wanted to measure sea ice cycles using a traditional way. Well, he used the old-fashioned way to measure sea ice cycles. Uh, I um, I was the person who helped him because in in early winter it is fine. It is easy to use this drilling bit to measure sea ice to drill a hole with just by one person. But as ice grows, it was very difficult for one person to do the work. So he two of us need to go out together to do this. And it was a very harsh environment. I believe I complained a lot. I said, even nowadays, we're in 21st century, are there any more convenient, easy method to measure sea ice thickness? And well, he said that's the only method he knew, and he believed it was very robust, reliable. Um, I'm a geodesist, so I believe that we might have better ways to measure that. And I proposed to measure CI thickness in a different way. I said, what if we install a GPS GNSS receiver on the surface of sea ice, and we track the vertical component of this GNSS antler. Well, he did not really know how accurate can we really track a point. I said we could perhaps track it to a level of with a precision of a few centimeters, or sometimes even better. So we try this. Um, we collected data and compared all the CI's cyclic retriever using geodetic method and his method. The way is we install a GPS on CI surface and use a laser ranger and sometimes tape measure to measure the antler height. Um, at the same time, do kinematic processing to determine the antler's height. Under sea ice, there was ocean bottom pressure sensor that was used to measure sea surface heights. Well, earlier I mentioned that one of my major duties was to maintain this pressure sensor. Um, um, if we know the elevation of sea surface and the elevation of ice surface, well, we can then estimate the freeborn by making us an assumption about the um, the ice hydrostatic equilibrium state. And then if we also measure CI density, seawater density, or make an assumption, we could calculate CI cycles. I think these two techniques they match reasonably well. At that time, I did not know we could track surface elevation changes using GNSS-IR. And inspired by McCann, after reading McCann's paper about using GNSS-IR to quantify near-surface subsidence, and after reading a few papers published by Christine Larsen, I record the experiment I did many years ago. So at that time, um, there were some limitations in doing this experiment because our expedition leader he was not so happy for us to go out to sea surface frequently because he believed it was unsafe. So after learning that GNSS-IR can track surface animations without going to install some sensors on the sea surface, then I believe that I could optimize the experiment. Here, the panel on the left illustrates the way of traditional GNSS-IR for sea level measurements. The direct GNSS singular and the reflective singular, there's interference here, and then we could use the singular to noise ratio to estimate the oscillation frequency and use that to link to derive the reflector height. What if the surface is covered by ice? In this case, the singular would be mainly reflected from ice surface. Well, sometimes they're slow on ice surface. And similarly, we could do GNSS-IR analysis to estimate the height between the GNSS antler and the ice surface. Once we know that, if nearby there's a tide gauge that can provide sea level measurements, and if this tide gauge is datum controlled, then we could place the sea level measurements and the GNSS-IR measurements in the same reference frame, well, using the same datum, high datum. In that case, we can do a simple math to calculate the freeboard. That's what we could do. So in summer, well, when there's no sea ice, then we could use GNSS-IR to measure sea levels. And in winter, we can perhaps measure sea ice surface elevation. If there are tide gauge measurements, then we could recover sea ice freeboard and perhaps sea ice cyclists. By searching the literature, I found that Sun from Ohio State University, who did a similar experiment to measure sea ice cyclists in the Great Lakes region. And though in his experiment, he assumed that the GNSS-IR measured lake surface alumni represent sea ice, lake ice cyclists, which may not be so accurate because the above water component, it is only a portion of the total cyclists. So that's why it's relatively thin. That's his time series. But overall, this is a cool concept. So his research inspired me, and I try to apply the same method for sea ice cyclists measurements. Well, not lake ice. So here we also need to consider possible influence from ocean tides. Here on the left, this figure shows the place an image acquired in Antarctica in December 2020. This is the place near Ross Sea in Antarctica. There's a GNSS station, continuous GNSS station that was established by in Earthscope. Nearby, there's an ocean bottom pressure sensor under sea ice. Here, there's a benchmark that was used for datum control. They conducted calibration every once a year or once in every 2 years. So I believe this is a good sign. It provides an excellent opportunity for me to test the method. On the right, this figure illustrates the sensing zone for GNSS-IR. Because here this station, the antler is not so close to the coastline, so I have to use a relatively low sunlight elevation angles to suppress the influence of land reflections. That's why the sensing zone extends so far from the GNSS station itself. Um, I assume that many of you might saw some of the GNSS-IR result and the method to extract the reflector height. So here I show the result directly, not the process of how I did the data analysis. And here on the upper left panel illustrate the reflector surface height measured by GNSS-IR. We could see that it seemed to be relatively noisy, but even for these noisy time series, it seems that there's an annual cycle, and nearby there's a tight gauge. There were very limited calibration measurements, so still I made a similar assumption. Just use linear interpolation to fit the possible instrument-related drift. After that, this panel illustrates the calibrated water level time series. By doing math, one minus another, we could obtain the freeboard. Here, this shows the high frequency sea ice freeboard retrievers with an interval of about 15 to 30 minutes, I believe. If we calculate the daily means, then the bottom panel shows the result. Here, there's the red dots illustrate an alternative calibration methods. Well, in 2019, for some reasons, perhaps due to logistic difficulties, the calibration was not done for this tight gauge. So instead of using the traditional calibration method, I use GNSS-IR measurements during Antarctic summer. So the GNSS-IR measures water surface to compare that with tight gauge measure sea surface for the calibration. But anyway, this just so if you really want to know the detail about this, you can go and read the paper. Otherwise, for now, let's just look at the black dots. The gray bars represent the variations for each day. From this figure, we can clearly see the annual ice growth and ablation cycles. We can see that in Antarctic summer, ice freeboard became to nearly zero, but in winter, late winter, it became a few decimeters. This is equivalent to a couple meters sea ice thickness. Here on the right, if we also plot the some weather data, including the water temperature are measured by the tight gauge. This is an offshore bottom pressure sensor, so it measures temperature as well. And the air temperature, in general, the ice cycle correspond well with the center temperature variations. Here, for some unknown reason, perhaps instrument related, it seems that the water temperature there are some problems. But overall, we could still see that in Antarctic summer, water temperature was higher than the long winter temperature. And this rapid water temperature correspond with the periods of rapid sea ice melting. Here, some of you might have already noticed that there are some bimode or multimode distribution in the sea ice freeboard measurements. What has caused that? I try to look at the data more carefully. If you still remember earlier, I showed a map that the Maram here this is the sensing zone. If we plot the sea ice freeboard retrievers as a function of the azimuth, and then this is the result. For the bimode or multimode distribution period, we could see that it seems that there's a pattern there. It seems the freeboard results, freeboard values, they are location dependent or azimuth dependent. So I think this is evidence that sea ice in that region is not the thickness is not homogeneous. So it may change in space. Another interesting signal that was observed at this site was a large jump in early September 2020. So this jump it's about a few decimeters. If we use the typical ice and seawater densities, then this is equivalent to a couple meters sea ice, which is unlikely. Well, ice is unlikely to increase by a few meters in a very short period of time. Here on the left, this close-up views of the time series. Here, this smooth curve shows the time observations. Again, we use the GNSS-IR measurements, subtract the time measurements. The difference represents freeboard, and it seems this step increase occurred within a very short period, within like 20 minutes. Well, ice thickness is unlikely to increase by that much in such a short period. Particularly if you consider the water temperature did not really change significantly, the air temperature did not increase sharply. If you look at the air temperature, it seems that over that few days, it was relatively warm, and the wind was wind speed was high a few days before that, but later it's about normal. My experience in Antarctica was that in the coastal region, if the air temperature is relatively high, and then that's an indication of a slow storm. So though there's no direct meteorological observations, slow for records at that location, we interpret this sudden step increase as a result of a slow for event. There are two other lines of evidence that support this argument. First of all, if we look at the sunlight-derived brightness temperature maps, we could see that before the step increase, before and after this step increase, sea surface brightness temperature increased significantly. So it's likely that there's slower ice that was added to the surface in that region. Another line of evidence is from sunlight aperture radars on coherence maps. Here this panel G represents a coherence map of two sunlight two source satellite images acquired in late August. The coherence was relatively high, um, but if for a pair of images spanning before and after this step increase, the coherence dropped significantly. And after that, it remains relatively low. If we look at an optical image, here's an optical image, we could see that um, the places with relatively high coherence, these are the high mountains and bedrock regions. So snow is less likely to accumulate in this region. That's why the coherence remains high. But for the other parts, well, here this is the GNSS-IR sign. For this area, um, the sudden decrease in SAR images coherence appear to be affected by the added surface material, for instance, slow, and that could change the coherence. Well, that's about using GNSS-IR for sea ice freeboard measurements. Um, At the same time, we also need to consider GNSS-IR is an effective tool for sea level measurements, even in the polar region. Um, Here, this slide shows the result, the work reported by Tabibi in 20 and his co-authors. It seems that um, in the polar region, there are some GNSS stations that are suitable for GNSS-IR studies. And the authors use this technique to measure polar coastal regions ocean time. Here is on the right. This shows the results on the power spectrum density distributions of the result derived from GNSS-IR and nearby tide gauge in Antarctica, well, in Antarctica Peninsula, so at Palmer Station. Overall, we could see that the in both traces, the the diurnal and semi-diurnal powers, they are really strong. So which means GNSS-IR can effectively capture the diurnal and semi-diurnal tidal constitutes. At higher, well, lower frequency components, for instance, monthly, semi-monthly, or longer time series, GNSS-IR did not seem to work very well. And it is perhaps, well, for instance, one reason, and the ice growth, ice cycles might affect the long term, the relatively long period tidal measurements. But I think from this study, we can clearly see that GNSS-IR can provide effective measurements for some tidal components in the polar regions. Another study led by Darn Jason at DTU, who used a GNSS-IR station in northwestern Antarctica to measure interannual sea level variations. They compared GNSS-IR measurements, tide gauge measurements, and satellite altimetry. And they concluded that these three techniques they agree with each other. Well, they are inconsistent. They could measure the trend and their annual the interannual sea level variations reasonably well. In their study, they simply assume that by averaging, well, detected GNSS-IR measurement and averaging them could represent the annual means, which which might be affected by CI cycles if there are interannual variations in CI cyclices, then this method might be biased, the GNSS-IR results. Well, if the CI's cyclics is the same in each year, in every year, then perhaps the at least the trend is consistent. But it is difficult for a certain region to always have the same CI cyclics. Um, and Christine Larson, she was interested in looking at this site as well, and so she wanted to analyze this site, and she talked with me and asked me if I could take a look at that. I look at the data collected at this site. It's great that there's a tight gauge nearby, and people from Denmark are well, the DTU personnel. They go there and do datum control regularly, well, nearly annually. So it's a good site to compare our sea level measurements between GNSS-IR and the tight gauge technique. So I look at the data and I find the two techniques they match pretty well. Both techniques can capture short-term tidal constitutes, though something interesting was also observed in the results. For instance, during Arctic summer and Arctic winter, the difference between these two techniques. Well, here the tight gauge is on datum control. So the two techniques, they are placed in the same datum. But then in summer, it seems that the two techniques, there's a bias between tight gauge measurements and GNSS-IR results. And then the bias is also the amplitude of the biases is it's frequency dependent, so which is very interesting. And in winter, we could see a bias. Well, of course, there's a bias because there's sea ice coverage. So sea ice cyclists would here in my previous study, I assumed that represent the IceFreeboard. But again, it is perhaps frequency dependent, though the difference is less significant compared with the winter, compared with the summer measurements. So which is very interesting. It's very likely to be associated with surface characteristics. But then because there's a tight gain here, what if we want to compare GNSS-IR with tight gauge measurements? Obviously, it's perhaps not consistent if we use the GNSS-IR measurements during Arctic Greenland winters, because sea ice may affect the high measurements. Instead, it would be great if we can compare apple with apples. So it means if we can compare GNSS-IR measured sea surface, so sea surface height, and tight gauge measured sea surface height. But then how to tell if the reflecting surface is covered by sea ice or is covered by seawater? If we look at the amplitude of the singularity noise ratios periodograms, we could see that there's contrasting amplitudes in summer and in winter, at least for that side. Here, this panel illustrates the Lambsgago periodograms amplitudes. It's plotted. It's color coded by different sun-like constellations. It seems that the annual cycle is also exhibited in the amplitudes. And if we look at the same GNSS constellations, it seems that there's a very strong this frequency dependent dispersion in the surface height measurements. Um, Again, this is likely an indication of something that is affecting the GNSS-IR height retrievers. We interpret this as influenced by surface characteristics, such as the dielectric constant. Though I'm still investigating this, I hope to find a certain model that could really model or characterize this kind of the influence of this the frequency dependent dispersion. Well, for now, if we just ignore the reason behind this, we could clearly use the amplitude of LSP amplitudes to separate ice-free and ice-covered periods. If we can identify this period, then these provide opportunities for direct comparison between GNSS-IR and tight gauge measurements. Based on that, we could really rely on the contrasting behavior and then identify a certain period when the amplitude is significantly lower than the typical LSP amplitudes, and use that to select the ice-free period. So here, this shows the density cumulative distribution function as a function of the amplitude. It seems that it is nearly stable for a certain period. There's no significant increase or decrease during Greenland summers. So we believe that there's a very narrow band that could be used for us to mask out the ice-free period. By doing that, if I plot this the ice-free period here in this is covered by red color. Well, means it's warmer, and the blue represents the period of ice-covered months. We could see that there's a clear ice growth and ablation cycle again, but even for the same GNSS constellation, there's this frequency related differences. We could see that. All right, almost done. So this is well, I'm still hoping to find a way to quantify this kind of why there's such a bias. But overall, this reminds us if we want to really compare GNSS-IR measurements, a lot of times we hope to use more data, so we want to combine different frequencies. But we need to be very careful when combining GNSS-IR retrievers from different bands. Here, this figure in actually the long time series, we could see that over nearly 70 years, there's the ice growth and ablation cycle is very clear, though different frequencies, different satellite, maybe there's a small bias. But then, based on this, we can identify the periods where there when there was no ice coverage. And if we compare that with tight gauge, this figure is actually the comparison between tight gauge measurements and GNSS-IR. It seems they agree on the order of a few centimeters. And if we if we calculate, we use the time series to calculate the summer means, we could really derive the interannual variations and long-term trend. Here, well, panel D plots the geocentric sea levels, and the bottom panel plots the relative sea levels. It seems that the trend they agree reasonably well on the order of a couple of centimeters, but still we could see very strong interannual variations. This reminds us that if we really want to obtain reliable long-term trends, we must have sufficiently long data If we just use this period, the first 10 years, we might think, oh, sea level, local sea level is decreasing, but in recent few years, it was increasing. Here are the conclusions. Thank you, and if you have any questions, please let me know. Thanks.
All right, thank you, Sorry,
Mhm.
for your nice presentation. So you
All right.
showed one of the early application of GNSS-IR for sea ice freeboard measurements. That's cool. So I know it's very challenging environment, right? So it's working with GNSS-IR, it's definitely not easy. So you have done an amazing job. So we have time for a few questions. We have 8 minutes for questions. So if there is some points and discussion and questions, you can post your question in chat box. Please feel free to do so. And until then, perhaps I can start by asking a few questions. And the first one is that how many of the available GNSS site is useful for sea ice freeboard measurement in polar area? So you show us the one in Antarctica and one in Greenland.
Right. So here this is a map summarized well by Tabibi. There are a few others. I think that are also fine, but very few. These are the eight of well, these are eight of the best quality sites, I think, with relatively long time series. There are some other sites, including here, TUL2 site is omitted here, but there are a few others. And then I think most of them they can be used for sea ice freeboard measurements, particularly if there's a collocated tight gauge. However, it's not all of them have collocated tight gauges, but it's also good to look at the. Here I have another map.
So
Here
for those sites are not collocated, so can we still use um, tight measurements by GNSS-IR to do something with
Mhm.
sea ice freeboard or
It
not?
will be challenging, but it is possible if we only want to know the overall the interannual
Hmm.
variations. For instance, if you look at the ocean tide gauge model in the polar region, um, some of the short-term, the high frequency tidal constitutes, they have relatively high amplitude. But for the longer term ocean tide, like the annual tide, the amplitude is pretty small, very low. If we only want to know how large the annual variation of CI freeborn is, then we can perhaps use a tide model or just use a GNSS-IR derived tide model to predict uh, the um, the water levels time series, which means it may be biased by a small amplitude
Hmm.
tidal constitute, but still it reflects the annual ice growth cycle well. Here on the bottom, I show some of the result. This is the black and the red trees. Industry is the one I derived using GNSS-IR only without using a tight gauge. We could still see the annual ice growth cycle and the amplitude. I think we could capture the annual amplitude of ice growth pretty well.
Yeah. So all right. So
Mhm.
tight here is a one, let's say, um, conflicting factor for sea ice freeboard measurements.
Right.
Are there any other factor like I don't know, waves and like significant waves or other things that, like currents?
Yeah, those might affect this, but similar to GNSS-IR, GNSS-IR might not work that well if sea surface is very rough,
Mm,
right? But
yeah.
then in the polar region, if the surface is covered by thin ice, it's unlikely to have very rapid variation. Like it's kind of like I spent more than a year in Antarctica coast, so I did not feel like wind or ocean current would be a limiting factor for GNSS-IR measurements of sea ice freeboard.
Yeah. So there is I've seen that you show a picture of your field work doing the hard job in the Antarctica. So is there how do you how do we validate what we get from Genesis IR for sea ice freeboard measurement? So is it like satellite data sets that they use, or is
Right.
there any kind of in situ measurement that
It would be great if nearby, if we do an experiment,
mm,
we drill this drill boreholes and measure sea
mm,
ice freeboard frequently. But it is difficult. Perhaps someone read our paper would be
mm,
interested to do such a comparison. Then there are other possibility, other opportunities for us to do some comparisons, not the direct comparisons. For instance, in Ross Sea, there are other studies about using borehole measurements and using the freeborn, the lead freeborn, well, the satellite altimetry method to estimate the freeborn. In general, um, their amplitude, they are about the same, on the same order. But still, I do not really have a very high and precision comparison between these two. But then, I think the GNSS-IR measurement is reliable. If we use, I compare the GNSS-IR measurements in this region with IceSat-2's measurements.
mhm.
We could see that in general they agree on the order of perhaps on the upper end of a decimeter.
And noting that Genesis IR is kind of emerging geodetic technique, right? So we are still
Right, right,
making the development and improve our
right,
model. So I was very it was very interesting to see how the surface responds to the different frequency of the multi-GNSS and those models that can explain the surface characteristics of the reflection. I think that's the beginning, and I'm hoping that Genesis IR measurement would be sometime very soon as a validation in situ measurement for satellite measurement,
right,
in
right,
particular for sea ice report measurement.
right, right.
That was pretty interesting talk, Suri. I really appreciate that. I see no question in the chat box. Yeah, and yeah, I think our time is almost over. So,
Mhm.
yeah, again, appreciate sorry for your time and for your
Mhm.
talk. So, again, thank you all for your attendance in the Zoom in webinar, and I'll send out invite for the next talk in the spring. I need to organize that through the mailing list, and yeah, I hope that you have a good day.
I saw there's a person who asked a question.
Oh, really?
Yeah, and
Uh, is there? I don't see a chat box
I
questions. All right. Yeah, yeah. Sorry. Yeah, there is here.
yeah, and
Okay.
here is
Yeah.
that. Okay.
Uh, yeah.
Thank you for this. Yes, I'm so
Yeah. Go ahead.
what's opt all right. So for the first question, what's optical way to set amplitude and peak to noise ratio parameters in your
Mm,
processing strategies? Well, first of all, for this highlighted, I did not use GNSS Reflect, but then I currently using that, but in the presentation, I did not really use Christine's software. I think the way to set amplitudes is you really have to play with the data. In my 2022 paper, I plotted a curve similar to the L curve we use for geophysical inversion. Um, for the peak to noise ratio at a certain level, you decrease the threshold of that. It would you increase the threshold. It will eliminate many of the retrievers. And then if you got very few of the results, very few retrievers, then you can't really quantify
no.
the innovation very well, right? So you have to play with it and see, find a good balance between the number of retrievers and the quality of the results.
Yeah, and this also depends on the number of the observation, like
Right,
the
right,
elevation angle. If you're using very low elevation angle, you
right,
don't retrieve high amplitude
right.
and
Yeah,
large picture noise. All right, and next question. And what distance from the coastline and what altitude can mean sea level be reliably determined from a GNSS station measurement in polar region? You showed the site ROB4
mhm,
collocated with tide gauge, which is distant from the coastline.
right. So normally, again, it's really depend. I think you have to plot. I always for all the GNSS-IR study, I always plot this on a map, and just to get a very rough idea about how far you can you should set you should limit your
Hmm.
sensing zone. When it's very close, it might hit, it might be affected by land returns. So you have to plot this on a map to take a look. And also you can just change your parameters, the limit, change the range of the azimuths and the animations, and then look at the quality, and eventually
Hmm.
find a good range of animations that would affect that will determine the how far your reflecting zone is to the coastline. Yeah, for
All
this
right.
side, yeah, this one is well, if we close, if we zoom in, it's a few hundred meters, I
Yeah.
believe.
If it's far from each other, to the benchmarks tide gauge and the Genesis can see also different VLM, and that really
Right.
bias the results.
Yeah, yeah, yeah.
All right. Okay. Thanks. It appears that there is no more question in the Q&A, so now we can say goodbye. Sorry, I missed the Q&A question. It didn't show up in my chat box.
All
All right.
right.
Okay. Now we can say goodbye and
All right.
have a good day. Yeah. Take care and
All
bye
right.
bye.
Thank you. Thank
Bye
you.
bye.